Let's just jump right into it. For years, this idea of the black box has totally haunted the world of artificial intelligence, right? You feed data in, something unimaginably complex happens inside, and boom, an answer just pops out. Today, in this explainer, we're going to look at how AI is rapidly evolving from those simple consumer tools into highly complex operational systems. And as we'll see, relying on that old black box model, it's no longer just a minor inconvenience. It's actually becoming a critical bottleneck. Because when AI starts making high-stakes decisions, we absolutely have to know exactly how it arrived at them.
There's a profound insight from recent research that perfectly frames our focus for today. Trust is not a button. It is not a disclaimer underneath an output. Trust comes from architecture. As AI gets more autonomous and tightly integrated into serious operational environments, we can't just cross our fingers and hope for transparency. We have to understand exactly why transparency requires deliberate system design. You literally cannot just tack trust onto the very end of a process. Transparency and reliability must be engineered into the actual architecture from day one, or the whole thing just remains a black box.
To unpack this massive shift, here is our agenda. First, we'll move beyond the black box. Second, the escalation of AI agents. Third, engineering trust. Fourth, building a control plane. And finally, the future of AI teaming.
All right, starting with part 1, Beyond the Black Box, drawing on foundational research by Jeffrey Grooms from 2019.
To really grasp this shift, we have to look at the stark contrast between two very different environments. Think about consumer AI. It's basically a simple black box. You ask for a pancake recipe, you get a recipe. Simple, right? But operational AI, that is a whole different beast. In a tactical environment, the system is processing massive amounts of variables, it's building situational knowledge, identifying alternatives, and prioritizing resources. In those high-stakes scenarios, getting a simple output without any context isn't just unhelpful, it's potentially dangerous. The machine has to support the human making the call, not replace them entirely.
Which brings us to this really powerful realization from the source material. The intelligence may be inside the model, but trust has to exist outside it. Think about it. Once an operational AI is generating dozens or maybe even hundreds of different alternatives for a really complex problem, raw computational intelligence isn't the bottleneck anymore. The real bottleneck is the human operator trying to figure out why the machine prefers one specific course of action over another. Basically, if you can't see the why, there is no way you can trust the what.
Moving on to part 2, the escalation of AI agents, looking from the present to the future. AI's role has escalated incredibly fast. It used to just tell us what was happening, but now it's predicting consequences. Just trace the evolution. First, computers collected information. Simple enough. Then, machine learning let us classify it. Next, AI started prioritizing that information for us. Pretty soon, it was generating alternatives. And now we're at step 5, predicting consequences. Every single step forward here drastically increases the complexity of the system. What starts as a basic data retrieval tool snowballs into this massive architectural puzzle where the machine is suddenly juggling endless variables across multiple possible futures. That architectural puzzle became crystal clear during a 2022 research project called RAID. The researchers had to completely shift the architecture because they changed the fundamental question. They weren't asking the machine what is happening anymore. Instead, they were asking, what happens if we do this? They tasked the AI with evaluating the consequences of multiple possible futures all in real time. And when you ask a machine to essentially simulate the future, you fundamentally change what that system absolutely has to be capable of showing its human operators.
Which leads us to part 3, engineering trust, diving deeper into that 2022 WRAID research.
When you have an agentic system running these incredibly complex, multi-step simulations, you cannot just accidentally build a trustworthy system. The researchers are adamant about this. Trust is a systems requirement, not a communications problem. This hits the nail on the head as to why transparency requires deliberate system design. You can't just slap a big green approve button or a tiny text disclaimer at the very end of a workflow and call it a day. Things like transparency, explainability, and interpretability, they have to be foundational. If the system wasn't deliberately designed to show its work at every single step, no amount of flashy user interface design is going to make up for that hidden data.
This comparison brilliantly illustrates the danger of hidden states. A standard chatbot workflow is basically a straight line, right? Human asks, machine responds, human reads. But in agent architecture, it takes an objective, breaks it down, retrieves data, analyzes it, delegates to other tools, replans based on new data, and then finally acts.
There could be dozens of state transitions happening entirely invisibly behind the scenes. If you only get to see the final answer after all that maneuvering, all the critical operational context is just gone. You have absolutely no idea what data it trusted, what it rejected, or what assumptions it silently changed along the way.
Let's look at a solution in Part 4, building a control plane for orchestration and trust.
So how do we solve this massive problem of orchestration without observability? The source material introduces a very specific architectural solution known as a control plane for intelligence, highlighting systems like Warden as a prime example. Think of a control plane as an architectural layer that sits right above and between all your different AI models. It's not just doing the heavy computing, it's observing all the participating systems. It maintains the contextual state. It actually understands which results matter, which information has gone stale, and how all those chaotic moving pieces relate back to the original goal the humans set.
But what exactly does this control plane need to show us? Well, for deliberate system design to actually work, the architecture must legibly expose some very specific elements to the operator. We're talking about the inputs, the provenance of the data, the decisions it made, its confidence levels, dependencies, and exactly where a human needs to intervene. By exposing all of this state data, the control plane answers the really vital questions, like which data did the system actually trust, or what remains unresolved. It's literally the exact opposite of a black box. It's total architectural transparency.
Finally, Part 5, the future of AI teaming, based on the 2022 Naval Postgraduate School Roadmap.
So, what does this highly transparent architecture mean for the humans actually operating it? Drawing from that 2022 NPS roadmap, one core finding is incredibly clear. Human-machine teaming is not human versus machine. It is not about keeping score of what task the machine can steal from the human. Actually, a poorly designed autonomous system will increase a human's cognitive load. If the system is just drowning the user in a sea of raw logs, constant alerts, confidence values, and just noise, it's failing. In that case, we haven't solved information overload, we've just replaced it with AI-generated information overload.
Instead of trying to automate absolutely everything under the sun, an effective architecture asks a much better question. What should the machine continuously handle so the human can make the decisions only the human needs to make? The ultimate goal here is to prioritize digital mission state and actually manage that cognitive workload. The machine should be handling the relentless, continuous tracking and the data fusion, isolating only the critical pivot points. That way, the human operator is freed up to make those high-level, context-heavy decisions that, quite frankly, only a human can and should make.
To achieve that kind of high-level support, systems are increasingly moving toward computationally exploring and simulating possible futures. And to do that, they have to rely on frontier AI mechanisms. We're talking about game theory for interactions among intelligent agents, utility functions for ranking alternatives when things are uncertain, decision theory for risk, and fuzzy logic for dealing with partial truths. These advanced mechanisms are absolutely essential for maintaining internal representations of complex, constantly changing environments. We are way beyond a simple chatbot interface here. This is real-time, multi-agent environmental simulation. But even with all that mind-bending complexity, we always come back to this guiding principle. The model can remain sophisticated. The architecture surrounding it should become increasingly legible. The internal mathematics of a single neural network, the exact weights and biases, those might always remain somewhat opaque to us. But the overall system, the architecture surrounding it, must be fully understandable and governed. We absolutely can design systems that expose the inputs, the state transitions, and the dependencies, even if the core model itself stays incredibly sophisticated.
I want to leave you with this final, provocative thought. As we look ahead to the next generation of intelligent systems, the true measure of success isn't just whether a machine can produce a wildly impressive answer. It's whether the architecture allows humans to confidently understand, coordinate, and completely trust the process that created that answer. That right there is the fundamental difference between a smart model and a truly intelligent system. Thank you so much for joining me for this explainer, and I really hope it changes the way you look at the future of AI architecture.